Okay, all right, let's get started. So the final exam, some of you asked, this is since our classes are Monday, Wednesday, 9:30 to 10:15, right? So therefore, according to schedule, we are going to be actually pretty early. December 10, okay, it's a Wednesday, 11:15 to 1:45. This is our final exam date and time. The exact room I haven't figured out yet because we're gonna need a bigger room for the final exam. So which means either we're gonna have two rooms or have one big room which can accommodate both the in-person and the in-person and the online session. So the location is to be determined. This is according to schedule, but the date is date and time is finalized. Oh, this is so mark your calendar. Publish this thing. Go to the online session. I'm gonna make the same announcement. 1 second. Final exam. Okay, so this is a final exam because there are quite a few students try to ask for the schedule. So here you are. Now let's continue from last class. So we in the last class we talked about matrix multiplication using the MapReduce, the concept. So the matrix multiplication, the first idea is to representing the matrix as two relations, right? So one is the M, matrix M, which has in the schema three schemas, I, J, and V. So I is a row number, J is a column number, V is a value. And then another is the N matrix, where it has J, K, W, right? J is a row and K is the column number, W is a value. So by doing this, we sort of explain matrix multiplication basically is a natural join followed by grouping and aggregation, right? So we have, this is like two MapReduce to to representing this is this operations. Now the downside for that operation is we have to do two MapReduce operations. Each MapReduce is representing like a one very input and output from the hard disk. So which is hard write and read, right, from hard disk, which is kind of time consuming. So the idea is can we combine this two step into one step, doing the matrix multiplication just in one step. So the answer is yes. So the downside for this one, everything comes at a price, right? So if you want to speed, then you need to have sort of like using the more memory or more space in your calculation. If you want to save space, you would need more time. So that's this is kind of like typical scenario for the algorithm is using time for space or space for time. So if you want to do the matrix multiplication in one step, you save time. Then the price you pay is you're gonna need a large memory to hold the matrix. The idea is for each element Mij in M, we're gonna produce the key value pairs Ik. Within this is a Ik. This will be the this is about the matrix dimension, right? Is so if you have a matrix M. Let's make sure the people on Zoom can see that. So if you have a matrix M, is I by J matrix multiplied by matrix N, which is J by K, then finally you're gonna have say like a P matrix. This matrix is gonna be I by K, right? So this is like basic linear algebra. Now if you want to do this matrix multiplication, there are So the definition for this is P I K, right? Represent for the rho I, and from K, this is going to be summation J from 1 to J, the M I J times N J K, right? So this is the definition for of how the matrix two matrix multiply. Now, this matrix multiplication can be represented as element-wise the operation. Okay, so what do you mean by the element-wise operation? So if you have two matrices of the same dimension, right? So you have in A is I by J, the matrix. If you see times B is the same dimension, okay, I by J. So then you have a matrix C is I by J. So that means Cij will be equal to Aij times Bij. Right? This is called element-wise operation. It's like basically it's the same coordination in the matrix A, and then do the operation on the same coordinate in the matrix B, right? So plus minus the times division or whatever, right? So you can do. So this is called matrix element-wise. So this is the element-wise operation. Okay. Now, matrix multiplication apparently is not the element-wise operation, right? Because when you do the matrix multiplication, you are not doing this is a one-to-one. You're going to do the operation on the same. So matrix multiplication is not the element-wise operation, but this is they are operations which is defined element-wise. Actually, is pretty useful. Like two matrices we sum together, right? So just sum up each corresponding elements in the matrix. Now, we can actually represent in the matrix multiplication, okay, which is not element-wise operation, but we can convert it into element-wise operations. Okay, so the idea would be like this. I'm going to draw a graph so you can see that is going to be better. So let's say you have an I by J. Okay, you have an I by J matrix. This is your M matrix. Is I by J, right? You have column is a capital I dimension. You have a J dimension for the I is dimension for the row. J is dimension for the column. Then you have this I by J the matrix. Okay. Now, suppose we can expand this is a two-dimension matrix into a three-dimensional array. Okay, three-dimensional array. So what you're going to do is you're going to make this to be a three-dimensional array. Then the third dimension will be dimension k. Now, for this you have a new matrix, right? So you have M, I, J, K. K is the one you demand. The K is just to representing the duplicates, okay? The duplicates in the original array. So then you expand this is a I by J matrix, which is M matrix. You duplicate like K times, right? Make it a three-dimensional array. It could be I by J by K dimension, okay? It's a three-dimensional array. So then this will be your new like Q3, okay? That means representing three dimensions. So M3 is going to be a new matrix. Then you have an N matrix. This N matrix is going to be like this. Originally, it's going to be a J by K matrix, okay? J by K matrix. Then what you're going to do is you're going to expand this is the I by is K by J matrix to also generate a third dimension, which is this is I dimension. So making this N matrix also to be a three-dimensional array, okay? Three-dimensional array by duplicated three times. So let's call this N3. So in this case, you have N3, the three-dimensional array for N is the first dimension is going to be replicated. So this is going to be equal to NJK, right? So this is going to be the small letter for representing elements. So everybody with me? So what do you do have? You have first you have a M matrix, which is I by j dimension. Then you have a N matrix, which is j by k dimension. Now what I'm doing here is you're going to replicate this is a M matrix k times, okay, by expanding from 2 dimension to 3 dimension by doing the three. So you have a third dimension, and then the third dimension is essentially just the replicate of the 2-dimension matrix, like mod k times, right? K times. So therefore, the M3 ijk is equal to Mij because they are the same, right? So it doesn't depend on k. Because k is a replicate of them. Then for the K matrix, originally it's a K by J matrix. Now you're just making it to be replicate this matrix by I times, but on the first dimension, right? So making it N3 ijk will just be njk because the I is you doesn't depending on the value, right? The I is that's dimension. So now you have M3 and N3. They are both 3-dimensional arrays of the same dimension, right? Is that clear? Yes. Now, if you can making this the elements multiplication, okay? Elements the operation. Let's say you're making this P3 ijk will be equal to M3 ijk times N3 ijk, right? So now you're making the matrix-wise, elements-wise modification between this is the 3-dimensional array. So what you're gonna have is this is a new dimension, right? You're gonna have this is a okay, I can just go back here, okay? So inside the room, you can still see. So you're gonna have this matrix is gonna look like this. So this is going to be I, this is going to be J, this is going to be K, right? So this is a 3-dimensional array. So this is called P3, okay? This is 3 dimension. With given this is a P3 ijk will be equal to M3 ijk times N3 ijk, okay? So you can do the matrix, you can do the elements-wise the multiplication for this one. Now, once you have this, okay, once you have this, what you're gonna do? You're gonna squash. You're gonna squash. This is a P matrix along the way on the J dimension. Okay, so you're gonna squash it. You're getting a J by K, I by. So this will be the I. This will be the K, right? You're gonna get the I by K dimension, the matrix. So in this case, you're gonna have P. You're gonna have a P matrix, which is Pik will be equal to summation j from 1 to j of this is a P 3 ijk. Then this Pijk would be the matrix multiplication of M and J. They're the same. Okay, they're the same. So what are you doing here? What you're doing here is basically you augment. Okay, you augment your 2-dimensional matrix to become a 3-dimensional array. And this 3-dimensional array will be multiplied elements-wise with this is N-dimensional array, which is also augmented to be a 3-dimensional array. Then by doing that, you have a new 3-dimensional array, which is called P. And this P is coming from elements-wise multiplication of M3 and N3. Once you have this, you squash it. Okay, you squash it by compress this is a P matrix along the J dimension, which you have this guy. Okay, which have this guy. Now as you can see, this will be exactly the value as original the matrix multiplication. But now what we're doing here is by converting instead of doing using this formula, but we convert it to a matrix-wise operation. Now, elements-wise operation, it could be very fast. Okay, it could be very fast because then, say if you can load this matrix into like a two matrix, then what you do is just using the your pointer just scan through the whole array, which is going to be extremely fast. Now, the using this, okay, using this. we can actually using this, we can actually design the second algorithm, which is we're gonna use in the making this metric multiplication in just one step. Okay, we do it in one step. So what we do here is for each element Mij of M, we're gonna generating key value pairs Ik Mj Mij. So this step, okay, this step essentially is this guy right here. We're augmenting the three-dimensional array because for each element in the M, we replicate the k times, right? We replicate k times. Okay, so the first step here is we basically replicate any value in the M matrix if it has a value, right? Because M could be a sparse matrix. It doesn't have entry or values on every position. So if it has a position, we're gonna replicate it k times. Okay. Now, then for each element njk in the N, we're gonna produce a key value which is Ik, which has njk, right? So this step is basically we are duplicate this. We're doing this the augmentation of the N matrix to a three-dimensional array, right? Because for each element njk here, we duplicate that I times, right? We duplicate I times. Okay. So then this is the first step. Map step essentially is doing this converting this two-dimension array matrix into a three-dimensional array. Then for each key of ij, you're gonna have associated list of this is mj, mij, and njk, right? For all the possible j's. So the reduce function essentially is just to multiply this is a two value for the ik. If they have the same j value, we just sum it up. Okay. So and then this is the reduce function is essentially is corresponding to do the element-wise multiplication and then squash it. Okay, then squash the matrix. That's how it works. So this is by doing this. I hope you can connect this is an algorithm here with the graph on the whiteboard, because then with that you can basically can see you can like visualize why we're doing this. Okay, because first time why going through this algorithm, I think it's pretty confusing for the students just to read the text. Although I think it's pretty clear, but it doesn't quite understand like why want to do that. What's the intuition behind it? Then I developed this is the visualization. I think now this should be much clearer. There's essentially this would be a map step. This would be your reduce step, right? So you can should be no issue. The downside, like I said, is you are using more space. Okay, you save time because now you're only doing one map reduce the step. You're saving time. And then the downside will be for every element like Mij, you have to replicate it k times. Okay, you have to replicate k times. Now, not all the replication, what you did here will be used for calculation. Okay, because it depends on each value. It depends on whether in the corresponding position, the j position, there is a value in the N matrix or not. If there's a corresponding value in the N matrix, then this entry or this is a key value pair will be used for calculation. But the majority of them, actually you just replicate it, but you are not going to use it for calculation at all. Okay, so you just duplicate it. Yeah, just keep it in there because you don't know which j, like in the N matrix, which j position will have value, right? To compute with, like using this as if we want to do this is a computation, it has both should have a value at the j position in order for them to match and do this multiplication, right? But if the matrix is sparse, you cannot guarantee like every j position they're gonna match. But of course, if you have dense matrix, you will have then every element here will be used for the calculation. But if your matrix is sparse, then you are not guaranteed to have every element will be used for calculation. So therefore, there are many. There's a duplication actually generating a lot of the entries, QL pairs, which you probably will not be used. Okay, but then this is you just keep things here for the in case you have a corresponding elements in a matrix. The same thing, you are duplicating each njk value like I times, capital I times, right? Now, not all of them will be used for calculation. So there will be quite a bit of waste. You can see that, okay? That kind of like waste. Then you are taking more space, like if you're loading the matrix into the memory, that's gonna take more space. But then you save the time in the write and read for each MapReduce step. Okay, so that's what I want to say about this is a metric looking in one step. So any questions on this is for this? Is this clear? Or this is so the main thing is you kind of connect this is algorithm, okay? Connect this algorithm with this graph, okay? That's if you can see that, if you can have that visualization, I think it should be pretty straightforward. If you still have problem, understand like either the two-step algorithm or this is a one-step algorithm. You can like you should go through like a few more times, okay? Then you're gonna I think at the end you will get it. If you still have problem, you should come to see us, okay? See talk to TA or talk to me about this the algorithm. Yeah, so this is a downside because if your I or k is very large, that means say this is like a 10 to the it's like a billion level, so that means you have replicated one value like a billion times. That's this actually could be quite memory intensive, and so therefore it depends on the applications. Okay, so if you don't have any question from the on the material, so that's what we're done with in the like basic operations. So we talk about the like relational algebra, talk about metric multiplication. Now let's get into the PageRank, which is now PageRank. We all know it is so like the core search engine for the Google, right? So if you use Google, like then this is it's not exactly the same algorithm when they first developed it because they have going through many iterations, but the core idea is the same. Okay, so this is sort of like the thing behind every time you type a word keyword in the Google search box. This is what they do. Okay, so hopefully after this you're gonna understand this is a PageRank a little bit better, or understand a Google search engine a little better. As you can see, it actually comes up from a very simple idea. Okay, the PageRank itself is not a big like a mathematically or the concept is not a big innovation, but you can solve on within the right engineering tool. You actually can see how big Google now is grow up to be, right? So this is also I think it's quite inspiring from a simple idea to become to generate a huge business. Now, before we talk about this, you have to understand like in old times how people do the search. Like for example, Yahoo, right? You guys probably anybody in this room have ever used Yahoo before? You have used before, okay? I think that's Yahoo. Yahoo actually is it's actually not quite a long time ago, right? It's Yahoo was dominating the search engine like 30 years ago. It's like people use it. Well, many of you probably haven't even born before that. That's what I'm saying is you probably never really use it. Some of you have probably have using the Yahoo mailbox. So before Google, Yahoo is a dominating search engine in the internet. So at that time, how they do the search, right? It's very simple. You have in all the web pages, each web page is gonna have a few keywords, and then you just match up the keywords then to the so you type a search, right? So the t-shirt. So then you're gonna search out all the website and find a keyword t-shirt. Whoever has like highest related the keyword gonna come up at the top, right? Now with that, it actually become a very it become a system that is kind of easy to scam with, right? Because if you want to having because when you do the search, whoever come up the top, you think about your business, right? You're running a business. You want your website to come up to the first, second, third, like the top few web pages, right? So then people can kind of click on it. If your searches happen on the second page or third page, I mean, nobody gonna well, sometimes, but very few clicks on that. So the idea is you want your search to be at top of the result. So then to spam that, you know, in the website, there are contents you can show to the user, and there are content you can hide it behind, right? So you can use HTML, yeah, so you can hide that content. So, but when the search engine, they are scraping from the website, they don't distribute that, right? So just script the whole web pages. So there are people actually doing this is putting a lot of keywords, like different kind of keywords in the backend. Nobody can see it, but the search engine can see it, right? The ranking. So that is actually can making the system very easy to to have the so-called spam with. So that's why when used to using the Yahoo, when you do the search, I mean, a lot of garbage come up, right? Come up at the top. You don't even know what are those. So it's not that easy to use. Google was, I think Google was become popular in like 2003 or 2004 in their time. I mean, when I first used Google, I think the first time I ever used Google is like 2003. It just feel fresh, okay? It just feel fresh. It's just kind of like when you search it, on the top is almost exactly the thing you are looking for, okay? So apparently they're doing something right. They're doing something is way beyond just keyword, okay? So then the idea behind is they are now looking back is very it's kind of simple idea, but it's a powerful tool. So the idea behind the PageRank is if you assume a user just doing a random walk over the web, okay, website. So what do you mean the random walk? That means if your user start at a random web page and surf the web just by clicking the links, okay, randomly, because each website may contain some links to other website, right? So you're starting with some like random web page, and then you just click through. This is the links is attached to the website, and go and see where the link gonna take you to where you're gonna take. Is follow like 10 steps, 20 steps, 50 steps. So each step you're gonna go to a new website. And then what is the probability? Okay, that the person will arrive at a given web page. So this is kind of a neat idea because now you are not depending on the content of the web page. The content web page is still going to play some role there, but eventually the probability you're going to arrive, see you design a website, then eventually the people going to go to your website. It depends on whether your website has appeared in somebody else's website or not. If your website never appeared in somebody else's website, that means people think that website is probably not that important, right? If a lot of people reference your website, that means your website is probably important. That's why people try to. So then means the information is more useful. So the idea, this is more like a review system, right? So the Google this is a search engine or the PageRank is like review system. It doesn't depending on what you say, or it depends, but it depends less on what you say on your website. But depends more on how other people say about the website. Okay, other people. So that's so this is this idea. So the PageRank of a page capture this notion by like a more popular or a worthwhile page, you will get a higher rank. Okay, page rank is you can view the page rank of a page or web page is like a score. All right, it's a score. What is a ranking? It's a score, which is gonna every page will having a score being attached to it. Okay, then and that score it does not come out within like how but does not depend on content on your website on a particular website, but depends on how the probability of how other people, how the like a random the user by surfing the website can landing on your page, right? So that's a different. So the content of the page was judged not only by the term appear in that page, but by the terms used in or near the links to that page, right? So this can be used to avoid a term spam. The term spam is what I talk about. You can just like getting some key values, the key terms by putting on a website. If using like the old searching engine, that's actually going to making this is a this is easily you can boost up your ranking in the old system. But now it's not so easy, because now if you want to it's easy to manipulate the content of your own web pages, but it's hard to manipulate other people's the web pages, right? So that's a main point. So then the question is so now just like the term the TF IDF, right? The term frequency, inverse document frequency idea. We have intuition. I have intuition, which is like the term which is the most useful or most important distinguishing the documents are the ones who are rare, who are less frequent in the documents, but appear has a lot of frequency in a particular given documents, right? So that's the idea, and we develop we actually having this is a developer algorithm. We're calculating the value TF IDF from that to making that. Now here is also this is intuition, right? This is intuition. This is idea. But you have intuition is not enough, right? Because we need to implement it. We need to get into a concrete calculation or concrete program to implement it. So now the question is how do we convert this idea or this intuition into something which is concrete, right? To do that. So I mean, I want to encourage you guys to think a little bit, right? So if you have this idea, you say your web pages, you don't want to judge it by the by its content, but you want to judge it by how other people say about your website, right? By using the link, how will you do it? Right? How will you do it? And then this is it can come up. It can come up. This is like a research, okay? Well, like most of this is like a real world problem. It's like this: you come up with some simple idea or some kind of simple concept. Then, based on that concept, you're going to think about how can I solve the problem? What is the best way to making that to implement it, right? So that's this is just like many of them. This is a PageRank is no exception, right? It's come up. It started from a simple idea, then we can build up on it to make that. Now for the web pages, if you want to visualize it, okay, then this is this is how internet actually looks like, right? So you're gonna have this is some website you're gonna point to CNN, right, which is like news. Some website you're gonna making this to be CNN, and then CNN may some article may reference to the Wikipedia, and the Wikipedia, then this is the New York Times also may go to Wikipedia, and this is something else. So in the internet, I don't know how can I silence this thing. Okay, just don't move mouse to it. So the internet, you can roughly view it as a big graph, right? A big graph, and this graph, it will have some website, well, some of links will have like sort of serving sort of like a hub, right? It's like a hub link. So a hub website. Hub means is kind of like is all be it all be this is called vertex, right? In the graph described. So it is a node which having many other node. You're gonna point to what is receive is many. This is links coming in or out of this particular node, right? So this is called hub. There are some other web pages which is like this one. They only have a link to the New York Times, but really nothing goes back, right? Goes back to it. So that means this is the less frequent, the website with less links will be less useful or the less important, but the ones within the more links coming in now will be more important, right? That means basically like Wikipedia is probably like one of the hub link. So that means people using a lot, right? So that's this idea. Now the only thing is the scale is huge. The scale is huge, right? So in 2015, roughly we have about 4.7 billion web pages out there. Like this is like index, okay? This index. This doesn't count like the dark web, right? So there's many web pages which are not reachable, okay? That of course, if you're not reachable, you cannot search for it. That's therefore we don't count that. So the dark website is kind of you can think about the island, right? It's like this is the mainland. There are some islands outside of this. There's a lot of them. So there are index web page, okay? Index web, roughly about like 4.7 billion pages. Now, 10 years after, okay, surprisingly, okay, like I already mentioned in the previous class, surprisingly, the total number of web pages did not grow much. Still in that 45 billion in the level. So that basically means each day there will be web pages like born, and then each day a lot of web pages going to be retired or so die. That's so it's kind of reached to a equilibrium state. Okay, it's like stable state status. So the scale didn't really, the scale of the website, it doesn't increase a lot, increase much. So it's still around like a 4 billion the pages, but still 4 billion, think about 4 billion dots in here, right? That's still a lot, okay? And now you have a graph basically has in like a 4 billion dots, and not mentioned they have like each one of them on average, like say you have about 100 the links to them. So that's that means we actually have that's a big problem. Now then the question is we from this graph or from this link we want to attach a score. Okay, we want to attach a score to each dot to represent the importance of each website, and then using that is a page rank. How you can do that? Now it's actually the math is actually pretty simple. Okay, but before that, let's give a formal definition to the PageRank. Now the PageRank essentially is a function, right? This function is going to assign a real number to each page in the web, or at least to the portion of web that has been crawled or its link is discovered, right? It's sort of like the index web. So the intent is that the higher the page rank of the page, the more important it is. So then no one fixed algorithm for assign the page rank, and in fact variation on the base idea can alter relative page rank any 2 pages. We're going to talk about this. We're gonna just talk about like basic the idea for the page rank, but now it has been evolving in the past like 20 years. It's actually become a very complex algorithm evolved around this basic idea. So once if you have this web and you have links, you have a score attached to each of them. Then when you do the search, it could be pretty simple, right? So if you search the say the Christmas gift, right? So you have in this the terms. Now it used to be depending on the content. Now once you have in this, if you have in this the page rank being attached to it, then what you can do is you can find out all the web page contains your term, and then rank those web pages by its page rank, by its importance, right? So there's one page which contains a lot of terms, but really nobody use that website. This page rank is going to be low, so it's going to be to the bottom of the search result, right? So that's then you can avoid this is a term spam in that case. So to calculate the page rank, we can use this so-called transition matrix of the web by representing using this graph. Say if you have like in this small web, we only have 4 links, right? We only have 4 links. So you're gonna go like this. So from link A, you can go to B, C, and D, right? To all of them. And then from link B, you can go to A and go to the D. From link C, you only can go to A, and from link D, you can go to B and C. Now, if you having this is a small web, then this web can actually be representing using matrix below, right? Using matrix below. So for each column, this is representing the starting web pages. For each row, it representing the ending links, right? So you can see from A, you can go to B, C, D. Then from B, you can go to A and D. From C, you can only go to A. From D, you can go to B and C, right? So it's the same information. So the only thing now is saying we having attached a value to the entry. So the value of each entry is depending on how many pages you can go from these web pages. Say from A, you can go to B, C, D. So then each of web page you can have 1/3 of chance. Right? You have 1/3 chance to end up. So therefore, this is the entry is going to be 1/3. From B, you can go to A and D. So then each A and D going to receive like a half the probability, right? So this is the transition matrix. Represent the probability. You can represent the probability from this page A to the other pages. Now you notice that diagonal elements is the probability of the web pages go to itself. There's none, right? So there's none. So that means it's from the page you cannot go to the cell. At least from this web pages, right? From this web pages. So the basic web page, the page rank is so that to calculate the page rank is actually like this. I suppose we started from random surfer at any of this n page of the web page with equal probability. So therefore, you're going to have an initial vector v0. That v0 will have in 1/n probability, right? Because so for when you try to do a random server on website, right? One random server on website. Then you're gonna have you start from v0. It's probably just have 1/n. Okay, n is equal to total number web pages. This is gonna be a small probability, but it's equal probability, right? So that just means you can equally starting you lined up on each pages. Now, if M is a transition matrix web, okay, transition matrix is defined as in this website, in this page. So is defined from the starting link to the ending link, and then you're gonna have the probability, right? You represent the transition probability represents some probability going from one link one page to another page. So this is by this probability. So if M is a transition matrix well, then after one step, okay, after one step, the distribution of the surfer will just essentially be M times V0. Okay, M times V0. So then V1 will just equal to M times V0. Okay. Now, then the V1 it will be having a distribution, you got a starting change. This is V11, V12 up to V1n. This V1 vector is no longer random anymore. Okay, it's no longer random anymore. Because if you have a page where is many people, many web pages point to it, then that the probability is gonna be enriched. So let's do the example here. Okay, let's just say this is 0, 1/3, 1/3, 1/3. This is 1/2. Let's just do one example. Okay, do one example. 1, 0, 0, 0, 0, half. Okay. So this is your M matrix. If you're starting at this is your V0. If you're starting at this is randomly, right? So then the next probability, the V1 is gonna be this. So for the first web pages, so when you try to calculate the probability of in the one step, you're gonna see from the previous step, right? From previous step, where did it come from? So there will be 1/4 probability for each one of them. This is gonna start. Then from the first page, you're gonna have in so in order to land in from page 1, okay, you're gonna have in from it could coming from second page, right? From the second page, and it has this the 1/4 probability coming from second page. So the probability in the second page, starting from second is 1/4. So then you have half of probability come from second page, and therefore that's that's 1/8. Then you can also come from the third page. This is 1/4. So this is 1/4 and 1/8. So for the first page, that is probability. And the first page is going to be 3/8, right? 3/8. Then for the second one, you're going to have for the second page, you can come from the first page or the fourth page, right? So what you're going to do is basically 1/3 and the 1/3 and the 1/2 then multiply by this by the 1/4. So 1/3 plus 1/12 plus 1. So that's a 1/3 plus 1/2 times 1/4. So this is a 2, 3. So that's a 5th. That's 1/4. So this is probably from the second one is 5/24, right? So this is from second one. From third one, it's going to be the same. So it's also essentially 5/24. The last one, the same. Right. So this is an equal probability for it's all at 1/3, 1/2. So you can see after one step, okay, after one step, you're gonna have then your probability is gonna change, right? So this is your new the probability. So you're gonna have more probability landing up in the page A because it's mainly because page A you have from the page C they have a unique pointer to that, okay? Because the C is going to A that with 100 probability. So once you're having that probability, okay, then the next step essentially it will be so the V2 is going to be M times V1, right? The transition probability times the probability in the V1 is going to be this is at M times V1. So this is going to be m times b0. Then essentially, because this is a magic operation, right? So you can do the association rule applies. This is actually become m times b0. So if we define the operation like the just like this is the m square. M square, that's just essentially is two matrices multiplied together, right? So then you can actually have V2 is equal to m squared times V0. So V1 is m times V0. And V3 I'm going to be equal to m to the power 3 times V0. That means a 3 matrix multiplication. And so on, okay, and so on. So in general, you're going to multiply the initial vector V0 by m, the transition matrix, a total of t times will give us a distribution of the surface after I step, okay? After t step, this is after t step. All right, so because then this is the distribution of the surface is going to approach to a limiting distribution V, okay? So if you having this is the surface, the probability, if you approach a limited distribution V or become a stable status, then the V is going to satisfy V is equal to m times V. Okay, if there's a such probability, V is equal to m times V, right? So then the next step is going to be m times V, which is going to be m times mv. This is equal to mv, right? So that's then the next step is going to be that's still going to be the cell, right? So this is called we reach to a stable status, right? This is a stable status, or we call it this is a limiting distribution, okay, limiting distribution. Now we can actually prove, okay, this is essentially is a Markov process. Markov process basically means what you're going to end up in the next step. It only depending on the previous step, right? Because say for example like V2, it will only depending on the V1, right? Depend on V1. V3 is only depending on the V2. So it's once you know the V2, it doesn't care. It doesn't matter what happened before, right? Like how you get to V2, it doesn't matter. As long as your status V2, the next V3 is just is fixed, right? It's fixed. So so the graph satisfies this so-called Markov process. And then if you have two conditions met, okay, if you have two conditions met, there is a limiting distribution. Okay, we're not gonna prove it, but we're gonna state that's a fact. The first one is the graph is strongly connected. Strongly connected means it is possible to get in from any node to any other node. Okay, so you're starting from a node. If you travel in the web long enough, you can get it back. Okay, you can get back to that node. So that's called strongly connected. Then this can happen. This happen for any node. Okay, if you want, you can any node, or if you from one node you can get to any other node. Is if you travel long enough. That's possible. So that's called the strongly connected. There's no dead end. Okay, node that has no arc out. Dead end, that means that node is once you get into, right? So if you have this is you have a node which only has incoming links, it doesn't have outgoing links. That's called dead end, because once you get into that link, you're gonna trap it, right? So then that's if you trap, then that's also a problem. So given if you have these two conditions, again, there's no dead end, the graph is strongly connected, then we will have a living distribution, okay, which means if you have the web is no matter how big it is, if we surf it long enough, we're going to reach to a stable status. In practice, for the web itself, we actually don't need to, because even you have a station or stable distribution, but it also depends on how long you get there, right? If you're taking like 1 million steps to get there, it's not very efficient, because then basically you have to compute this like 1 million times. But in practice, the good thing is in practice, 50 to 75 iterations are sufficient to converge within the error limit double precision algorithm. So if you serve this, basically this, if you run this algorithm 50 to 75 times, your page rank is actually enough. Okay, it's actually enough. Because what do you remember? What do you really care? What you really want is the relative ranking of each web page, right? You are not really into the exact probability for if you serve on a website, what exact probability of this is of this website, right? Like the probability, this probability is 0.995 or 0.995100001. Doesn't really matter because right, you don't want that precision. Basically what you really care is the relative ranking for the page. If you, as long as you know one page is more important than another one, then that's good enough. Okay, at least for some applications. So once you run this web page like 50 to 75 iterations, it pretty much can separate out your pages, like which ones are important, which are less important. You can separate them out. Okay, so that's in practice. That's why we don't need to get in that like the laser accurate, right? To calculate like for the probability, like every the decimal point. But it should be long enough to separate out the web page themselves. So you can see essentially this page rank is become a matrix multiplication, and this matrix multiplication is also it becomes the how do you say, this matrix multiplication, this is also becomes the multiplication of this transition matrix, right? This transition matrix. And this transition matrix, as I said before, are sparse. Okay, this transition matrix they are sparse. So which means when you try to fill in this here, if you're making the dimension to be like a 1 billion, 4 billion by 4 billion matrix, okay, 4 billion by 4 billion matrix, then the entry here, most of them are zeros, which means they are okay, from this graph. Okay, so from one website, one page, you point out the links coming out from page. It's probably like hundreds, right? Level hundreds, or like maybe 1,000. That's like maximum probably. So that means the given you have like 1 billion the entry, then you only have 1,000 come out of. Then this matrix is highly sparse, right? Highly sparse. And what we need to do is actually we need to do this matrix multiplication. Now, if you want to calculate m, say for example, m to the power of like 50, right? How many MapReduce you need for that? How many MapReduce job you think you will need? So like say each matrix multiplication is each matrix multiplication is a MapReduce job. So how many MapReduce jobs you need to do the? So this essentially is you just having m, right, times m. Then you have a result in modular m again and modular m again, modular m again, right? So you do this sequentially. You're gonna end up with the 50 times the m to 50, and then m to 50 modular v0. This is gonna be you're gonna have the v50, right? This is random server after like 50 times. This is how much. This is the limit distribution or the distribution of the probability for you end up with each website. So that probability is your score, right? Is a score. Now, if you want to do this, so the goal essentially the v0. This is just a random vector. This is a vector of the 1 over n, right? You don't need to do that n times. So essentially, if you want to get in the page rank after 50 iterations, or what you need to do is to calculate this m to the power 50, right? So if you want to calculate m to the power 50, say each matrix multiplication is one MapReduce job. So how many jobs you need here? 50? Yes. So you can do so the map reduced job 1 is you getting M2 equal to M times M. Then map reduced job 2 is going to be M3 equal to M times is M squared, and so on. So you have 50 map reduced job, right? So that's you can get it done. Okay, do it faster. So in here, this M, they are not really the M, they are not distinct from each other, right? So you can have M50. Once you have this M, you can actually calculate M times M, so you can have this M squared. So this M squared is actually a fixed number, right? It's fixed number. So when you calculate it to the M to the power 4, you have to go through M4 is equal to M times M to the power 3. You have to come from that row. You don't need to, right? You can just do M2 times M2. That's equal to M to the power 4. Right? So then you can actually go, this can grow like exponentially faster, right? So you actually don't need to, if you to the M to the power 50, you don't need like 50 map reduce. What you can do is you can do the M squared. So then this is 1, M to the power 4, then 8, right? 16. Then you do the 32, and then M to the power 40, no, 64. Actually, if you want to get a 50, I actually can get it to the 54 using like 1, 2, 3, 4, 5, 6. I can 6 step, I can get to this step, right? And this is better than M50, right? This is actually better than that. So you don't need this is you don't need like you to do this map reduce like the 50 times or 64 times in order to get there. You only need like six map reduce job, okay? So which is gonna make it your algorithm actually very efficient, okay? Very efficient. So as long as you can do one, all right, as long as you can do one, then you can do this 64 in a very in a pretty efficient way. Okay, so that's this is how you look at it. So that's this is mostly end up, although it's like 50 to 75 iterations, probably just end up with like 6 or 7 map reduce job. Okay, that's but each map reduce job is huge. Okay, it's huge because like I said, it's 4 billion by 4 billion matrix. You want to do the maximum allocation. That's a huge. Just want to show the person if you are on the Zoom. So this is essentially what I'm saying is here M. You can do the M multiply M. Right. So then M4 is then it's just to be the M2 multiplication. M8 could be M4 multiplication, so you can get into M16. That's 1, 2, 3, 4, 5, 6. Right, 6 map reduce. You can get into the M to the power of 64. That's pretty efficient. Okay, so this is so this is the basic idea. This is the basic idea for the map reduce and for the PageRank, how we calculate it. Pretty much. Yeah, this is these are the you now up to this point. Okay, up to this point, you pretty much know. Like for the basic PageRank, you pretty much know how to do all of them, right? Because we already talked about for the matrix multiplication, for the sparse matrix multiplication, how we do it. You already know it, right? So that's and then for the PageRank, essentially this is you just essentially it's just a multiplication of this transition matrix. Now you know the PageRank. So in theory, okay, in theory, you guys already can do the calculation. But of course, this is that's the big concept. Big concept is always easy to deal with. But in reality, there are always some issues here. Okay, you have to deal with like tie the end a little bit. So there are some issues are, for example, like why is a dead end? Okay, dead end is like in this graph, the node C is called a dead end. Dead end means when you only have incoming links, but you don't have outcome links. In the matrix, okay, if you put in this is the graph in the left to the transition matrix, you're gonna have in the transition graph to the left. So that means the column C, okay, this is A, B, C, D, right? Column 3, which is represented from node C, the probability are all 0. That means there's no links coming from this is a node 3, right? So therefore, the answer was 0. The issue with the dead end is if you surf through this then the limiting distribution is all zeros, right? So you can think about it. The long enough when you're surfing, this is just intuiting, right? When you surf this is a graph long enough, everybody can end up with C, right? Because it's like a black hole, right? You can absorb everything. Once you get in, you never get out, right? So that's so it looks like this is you should see and end up with C should be with probably 1, but actually if you do the math, it becomes 0. Okay, so it's so that definitely is an issue, right? Why we need to get rid of that. Now, as a matter of fact, this is like the general structure for the web. Okay, so if you want to if you really look at this web, this is how it looks like. So the web, in the center of it, you have this so-called strongly connected component. This is the part we want, right? Because that's because remember the two conditions. We have a leaving distribution. One, they have to be strongly connected, right? The second is no dead end. So the middle part, this is where we get most useful. Now, parting from this strongly connected the component, you also have this in component and out component. The in component will be those components. You're starting here. You can go into from this in component. You can go into this strongly connected component, but you will not get out. You want to get back to this. Okay, so this is you can have the in component. Well, those ones who can go into this as strongly connected component, but you cannot get back. You cannot get back, travel back. Out component, those ones you can travel from strongly connected component to the out component, but you can never get back to the strongly the connected component. Okay. Now, based on this in component, out component, you also have some. This is called the tendrils. Okay, you have this is tendrils out and the tendrils. Basically, this is tendrils out. If from in component, you can go into this component, but you cannot come back to this in component, right? So this is called going there. But out component, you also have this is called tendrils in. You can get in. This is from link to this out component, but you cannot go out. Now they also have this the tubes. Tubes will be you can travel from in component to the out component, but you don't have to go through this as a strongly component, just directly in component to the out component. Now, can we have the link from the out component to the in component? Or do you think I can have going from out component to this is why this is one direction? Can I go this direction? So what would happen if you have a link from out, if you have a tube from out component to the in component, what happen? Then it becomes strongly connected, right? All right, so if you have this, then it becomes strongly connected. So it should be included in here, right? So it's not there. So that's then when we're having this graph here, that basically means these are all in one direction. Okay. Same thing. You don't have anything like from in component to here, because if you have this is like a tendrils in to the in component, then this tendrils basically can go into the SCC. Then that should be in here, should be in the in component, right? because those tendrils are the ones you cannot go to the strongly connected component, right? So that's this is the same thing. So your web roughly can be of course there are some islands. The islands are represented out here. These are disconnected component, which doesn't even in this big graph. This island is not in the is like a mean graph. Now from here, one way to deal with dead end is we want to peel it off from the from this web structure web. Now from this like a tendrils in, tendrils out, in component, tubes, and the strongly connected component. Which part you think is like a useful, or which part you think we can assign the PageRank value to it? Apparently, strongly connected component, this part we can assign value to it, right? Okay. So what about this tendrils? Do you think we can assign this tendrils to them? To add value to the tendrils? Probably no, right? Because these tendrils out, these are representing the dead end, right? Because once you get into these tendrils out from here, you will never get back to a strong component, okay? So these tendrils out, these ones, we need to peel them off, right? We need to peel them off. What about tendrils in? These are also bad, right? Because this is the out component. These are the dead end, right? This is the out component. Once you get into the out component, you will never get out, okay? So basically, tendrils out and out component, we should take them out. What about tubes? Tube the same, right? Because this thing you also need to take out. Essentially, what we can do is like this in component. In component is fine. In component is not dead end, right? Because you can get in, you can start from here, you can get into the strongly component, you can still travel here, but you just never get it back, right? So in component is fine. Then you can starting from anywhere in the in component, you can still travel to the strongly component. So essentially, when we apply the PageRank, what we only we want to peel off or taking all those structures which are not useful in the PageRank. Basically, what we only want to keep are this in component and strongly connected component, right? These two components for the web. So we deal with the dead end. This one way to do is we drop the dead end from the graph, okay, and also drop their incoming arcs or links. Doing so may create a more dead end, which also has to be dropped recursively. However, eventually we end up with a strongly component. None of those nodes are dead ends. Okay, in the previous figures, recursive deletion of dead ends will remove the out component, tendrils, and tubes, but leave the strongly connected component and the in component there, as well as the part of any small island in there. So then we can modify the process by which the random server assumed to move out with the web. This method would propose taxation, right? There's also one problem, okay, with this is removing this dead end, because there is problem called spider traps. Okay, there's another issue called spider traps. This is this also can be an issue. Now dropping the dead end by doing this, right? If you for the upper graph, if you drop the dead end, then eventually you're going to drop out the E first. That E is a dead end. Drop out E first. Then after dropping the E, C also become a dead end. Then you can drop the C. Eventually end up the graph to the right is ABD, right? Now there could be another way to get rid of this dead end is if you have a C point to the self. Okay, this is called spider trap, because now there's a link coming out of C, but it's pointing to the self. Okay, so in this case, for the C, it will have an entry like if you back to here. Then for this graph, if we have a graph, the link come out of C from like this. So what you have here, instead of have 0 to the column C, you're gonna have 1 to here. This diagonal value is 1, right? Diagonal value 1. Now, this also created another, this is going to create the issue is once you have this spider trap, then every time when you get into the C, you can loop here forever, right? Loop here forever. So then this will be having a probability 1 you get into the C, right? So which you don't want, okay? This is give the C like the infinite the importance, but actually it's bad because some people may design like if you allow spider web, what people can do is they can just create like a page just have a link to the self and keep going, right? Now even worse to detect if it just link to the self, then that's actually easy to detect. You don't have I mean if any web page contains link to itself, you delete it. But even less to detect is you see I creating like a few web pages, okay, on link at different servers. So then I'm gonna creating a loop within this small graph, okay, within a small graph. Now, as long as there's something pointing from outside to this loop, it can loop inside forever, right? Loop inside forever. This is also a trap, right? This is also a trap. But this trap is very hard to detect because then you more than detect, you have to get in this is like full web, right? You have to find this is a local trap, okay? Or you can make it even larger, like 10 web pages or like 100 web pages. That's easy, right? To create a loop using this is a 100 web pages. That's pretty simple. But if you want to detect them, it's very hard because you don't know where this is 100 web pages come from. So therefore, by removing the simple spider trap, like if you have pointing the cell by remove it, you can solve like simple case. But for these complex cases, you cannot solve it. Okay. So therefore, we need a more the more advanced technique, or is called taxation. Okay. Okay. So now it's time. So we're gonna talk about this. Taxation is in the next class. Basically is just for every step for the transition. Not only getting from you also get a random start. Okay, that's how avoiding for the spider trap. And then we're gonna cover this and talk about the implementation as well. Okay, so that's which will be your project number 2 for your homework. All right, that's all for today. I'll see you guys on Wednesday.